Hi, in this video we're going to go over the worksheets of week 4 in sections 7.5 to 7a and some of the test review for the upcoming test 1. So first we want to explain how to choose a good U and DV when we're doing integration by parts. So the way that you want to do this is U is always selected as the function that is easiest to take derivative, and dv should be the easiest to integrate. Of course, I'll say that this one takes precedence. Find out first who is the easiest to integrate, and then if the other one you can find the derivative, then it's going to be much more easier to do. Then the other thing that you want to do is that once that you have the u times b minus b du, you want that this expression is not more complex than the original. That's how you know that you have a successful integration by parts. The worst case scenario, this is going to be of equal level of complexity or similar type of functions, but when that happens, then you can often very easily pivot to a formula where you have some sort of recurrency. So that's going to be the example number 2, where we have e to the 2x cosine of 3x. So in here, I'm going to pick u to be e to the 2x, and this is fairly easy to take derivative. This is 2 e to the 2x dx. dv is going to be cosine of 3x. And when we integrate that, that's simple as well. It's going to be 1/3 of sine of 3x. There's a small substitution in there going on. And when you do here the u times b minus b du, you find yourself doing 1/3 e to the 2x sine of 3x minus b du. So it will be again the 1/3 e to the 2x sine of 3x. So the thing is, this sine of e to the 2x sine of 3x, notice that it's the same level of complexity that this integral. And you're kind of trading the sine by the cosine, so it doesn't seem like you're making a lot of advancement. But what we have to do here is go back again and do parts for this integral. So if I'm going to do parts for that integral, I'm going to pick the same type of substitution that I did before. So it's consistent. U is equals to e to the 2x, and dv is going to be sine of 3x, and therefore b is going to be minus 1/3 cosine of 3x, and the u is going to be e to the 2x times 2. Okay, and so when I do the integration by parts, then this piece here becomes minus 1/3 cosine of 3x e to the 2x minus b du, and so notice this minus and minus a plus, and with the 2/3, and I get this e to the 2x cosine of 3x. And so you might be confused because you are getting again the e to the 2x cosine of 3x. And that is a fair question, but what you have to do here is that you gotta fold this with the original. What do I mean by that? Let's rewrite all this thing. So we have that e to the 2x cosine of 3x is equals to what? It's equals to 1/3 e to the 2x sine of 3x, and then we have minus 1/3, and now we're gonna write here everything that is in here. So we have minus 1/3 cosine of 3x e to the 2x, and then plus 2/3, and then the integral e to the 2x cosine of 3x. So because this is exactly the same thing as this, what I'm going to do is, well, these are the same terms, so I'm going to add them up. I'm going to put them together in the same place. If I multiply this by this, I'm going to get minus 2/9. So in the next step, I'm going to end up getting this is going to be minus 2 over 9. So here is going to be 1 plus 2 over 9 integral of e to the 2x cosine of 3x. Notice that I take this and I put it on the other side of the equality, and that's why it becomes 1 plus 2 over 9. Okay? And this is equals here to 1/3 e to the 2x sine of 3x plus 1 over 9 e to the 2x cosine of 3x. And so last, when you're trying to find out what the integral is, you have that e to the 2x cosine of 3x dx is equals to just, and this is going to be, and let me factor this, 1/3 e to the 2x factor sine of 3x plus 1/3 cosine of 3x. And then down here, I'm going to divide by this. This is 9 over 9, so 11 over 9. So I'm dividing by 11 over 9. And that pretty much is what it is. We really find a formula that is that comes from the iteration that we have from this two different parts that we took place, and then from getting this part to the other side and getting a consolidated number. Now this is the first integral from the worksheet. Now let's go for what is arctangent of 3x. Let me put this here below. And so now I'm gonna go for this. Arctangent, I do not have anything that gives me information about the antiderivative of arctangent, so I'm gonna just use parts because I don't know the integral. Of course, cannot be dv, but it can be u, because I certainly know what is the derivative is 1 plus 1 over 1 plus x squared. And so from the dv, I can just pick the x. And so b will be x, and that's going to certainly simplify everything. Then the integral from arctangent of x dx is going to be u times b, so x arctangent of x minus the integral of b du, and this is x over 1 plus x squared dx. And notice that this is a simple substitution. U equals 1 plus x squared, and so du is going to be 2x dx, and because I only have the x dx, is going to be du half, and so this is going to become x arctangent of x minus 1 half. And then because we're going to get 1 over u, this is going to be the log of 1 plus x squared, and then plus c. And so that's the end of that particular integral. Now we want to kind of do the same thing for trigonometric substitution. So we want to write the rules for integrating integrals involving sine, cosine, and integrals involving secant and tangent. And that is more, you gotta relate to whatever is happening, if it's odd or even. And what you do is you always leave one sine or one cosine to the side, depending on the substitution that you want to make, or one secant by tangent or secant squared, depending on what you want to do. So let me just, instead of writing this that you can review on the particular section, let me just showcase that with integrals 5 and 6. So for example, here we have sine cube and cosine square. So because this is the odd member, then I can kind of pull one of those aside, and then I'm gonna try that one that I'm pulling aside becomes my du and the substitution. Notice that I have now sine square, cosine square. And so it would be nice if I have everything in terms of cosine, so I can make a substitution that gives me a derivative in terms of sine. So sine square is 1 minus cosine square. And so if I do that, then this becomes 1 minus cosine square times cosine square times sine of 2x dx. And I can pick a substitution u equals cosine square. And I'm forgetting the 2x here. Let's not forget those 2x. U is equals cosine of 2x. And so the du will be minus 2 sine of 2x. The derivative of cosine is minus sine, but by the chain rule, I get a minus 2. So minus 2 sine of 2x dx. And so minus 1/2 du is sine of 2x dx. Okay? And so thanks to that, this integral is going to be minus 1/2, and then it's going to be 1 minus u square times u square times the u. And so this is like u square minus u to the 4th. And I can simply go back to saying, well, then this is going to be minus 1/2, and then the integral is u to the 3 over 3 minus u to the 5 over 5 plus c. And then, of course, replace what the substitution is. So this is minus cosine to the 3rd of 2x over 6, and then plus cosine to the 5 of 2x over 10. And that's it. That's for this particular integral. So everything is about separating the right part for the substitution. You gotta have the du in front for your substitution, and that's kind of the key with the trigonometric integrals. Here on the next one, we have tangent cube times secant square. And notice that because we already have the secant square, and secant square is the derivative of tangent, then the substitution is very simple. Use tangent, and the u is going to be secant square dx. And so this is going to just transform into u cube du. And that's it. Then this is u to the 4 over 4 plus c, and that will be tangent to the 4 of x over 4 plus c. So trigonometric substitution with powers, it just requires like you're able to play with whatever you're being presented in here. Okay? All right, so now let's transition to another exercise. Okay, so now for trigonometric substitution, we want to be using certain forms to know what trig substitution we want to use. So we have something of the shape a squared minus x squared. Then we have the substitution a equals a sine of theta. If we have a squared plus x squared, then we have the substitution of the type a equals tangent of theta, mostly because of the a squared plus x squared. And if we have something of the shape x squared minus a squared, then we have x equals a secant of theta. Of course, this is not necessarily something that you don't want to use the cosine, the cotangent, or the cosecant. You can do so, but you need to pay extra attention if you're going to be doing those. So now let's check some examples with that. So if we have 16 minus x squared, according to this, we should be using x equals 4 sine of theta. According to that, the dx is going to be 4 cosine of theta d theta. And so this integral here transform into 16 minus 16 sine square of theta. And so that is going to transform into 16 1 minus sine square, which clearly is cosine. So cosine square, I take the root of both of them, and it's going to be 4 cosine of theta the theta. And wait a minute, I forgot here to multiply by the theta. So I gotta multiply here by 4 cosine of theta the theta, 4 cosine of theta the theta. And so also here by 4 cosine of theta d theta. Cannot forget the d theta. Otherwise, I'm missing half of the integral. Okay, so this will be 16 cosine square of theta d theta. To just complete that, we gotta use the transformation of double angle. So this is 1 plus cosine of 2 theta divided by 2. And this is the easiest way to go about this. So this is going to be simplifying 8 times, and then we have the integral of 1 is theta, and the integral of cosine of theta is going to be sine of theta, but of course because we have this 2 here is going to be plus 1/2 sine of 2 theta, and then plus c, of course. Now, because we need to go back to the original variable as always, then we need to replace what this is. X over 4 is sine of theta. So, of course, arc sine of theta is going to be the result here. So this is arc sine of x over 4. And then plus 1/2. And we want to know what the sine of 2 theta is. But sine of 2 theta, instead, we can see it as 2 sine of theta cosine of theta, and we know that sine of theta is x over 4, so this is like 2x over 4, and then the cosine of theta is something that we get from the triangle. So if theta is this, and sine of theta is opposite over hypotenuse, so this is 4, this is the opposite, is x. And so the adjacent, of course, is going to end up being 16 minus x squared, sorry. 16 minus x squared. By the Pythagorean theorem, okay? So this is going to be that. And so at the very end, this gives me 1/2 of x, 16 minus x squared. And that is plus c. And that is the final transformation of this to values of x. Remember, we always need to go back to the original value of x. Now, number 9 is set up a form for the partial fraction decomposition for this. And we don't want to solve the coefficient. So we're not doing everything here. We're just doing the partial form decomposition. So this is x squared minus 3x plus 3. And we can factor the denominator as x squared times x squared plus 1. And so the partial fraction decomposition here will be a times x plus b times x squared, because we have repeated terms for x. And we also have a term here that is an irreducible. So we're going to have cx plus d over x squared plus 1. Sorry, this is not equal, this is a plus. And so this will be the partial fraction decomposition for this piece. Notice that we don't want to solve the coefficients, so this is where the exercises end. Now, we can go ahead and do this composition for this one to evaluate this integral. We have x squared minus x plus 8 over x cubed plus 2x. I'm going to factor that out, and this is going to be x squared plus 2. And so, of course, I can just check this decomposition as being a over x plus bx plus c over x squared plus 2. And then if I go to simplify this, x squared minus x plus 8 should be a x squared plus 2 plus bx plus c times x. Because I want to obtain the coefficients as quick as possible, then I'm going to get the values that simplify the better. This x equals 0 provides me with a 2a here and then 0 here. So that implies that a is equals 4. If I do x equals 1, then I get 1 minus 1 is 0, and I get that a is equals to 4 times 3. plus b plus c. So I get one equation in there. And I want to give another value that makes this simple. So I'm going to give x equals -1. Over here, this is going to be 210. And over here, this is 4 times 3 again. By the way, this is going to give me 12. So this is going to be -4 is equals b plus c. And for this one, I'm going to have c minus b time -1. So I'm going to flip this around again. And I'm going to have this is 12. So -2 is equals b minus c. Okay. So I get -4 is equals b plus c. And I get -2 is b minus c. So with this, I can eliminate c. And I get that -6 is equals to v. Or b is just going to be -3. And so according to that, if b is -3, then that implies that c must be -1. Once that we find all the coefficients, then we can go back to the original integral here. And this will be the integral of 4 over x, the x plus the integral of -3x minus 1 over x squared plus 2. And so at this point, of course, we get some pieces that are easy. The first integral is kind of easy. We can get 4 log of x. But for the second one, is going to be much more easier if I separate that. So I can probably separate this into pieces. So it's going to be -3 x squared plus 1, the x. And I'm going to have minus 1 over x squared plus the square root of 2 square the x. And I'm writing this in this way so you can see clearly that this is a trigonometric substitution that is going to give me an arctangent. So this is 4 log of x minus 3 times. The substitution here is going to give me a 1/2 here, and it's going to be log of x squared plus 1. And finally, for this one here, I'm going to use x equals square root of 2 tangent of theta. So because this is going to be the antiderivative, this is going to be minus arctangent of x over square root of 2 and then plus c. And so that's the end of this particular integral. If you have doubts about any of the steps, try doing this very carefully. This should be very easy with the substitution. And this will go with the trigonometric substitution basic for tangent of theta. X equals the square root of 2 tangent of theta. We've done this one quite a bit, so that's why I'm jumping directly to what the end result is. All right, now so we're going to transition to exercises in volume for review. So consider the region between the curve 1 minus x squared and the line 1 minus x. So normally you want to make some sort of picture to be able to tell how the function is behaving. So 1 minus x squared is pretty much like an x squared that is flip, and so minus x squared, but this 1 is going to make it go above, and this is going to be a thing where this is 1, and then it's 1 minus x squared is going to continue to be something like this, and then 1 minus x is a line that crosses here. So my picture is not really nice, but if you want to have a nicer picture, then you can probably use Desmos to just make a better graph. So for example, y equals 1 minus x squared, and then if I want to have y equals 1 minus x, then this is what I want. So it's just looking much better than what I have. Let me actually use this one for the video. Okay, so I'm using this, and of course the area that we want to use is this area that is in the middle here of things. Later, the thing is that we're going to actually use -1 as an axis of revolution. So we're gonna go and use the line -1 as a point where we want to do that. Initially, we want to do cylindrical shells, and you gotta remember that for cylindrical shells, we pick a piece that is parallel to the axis of revolution. And then I'm going to have this as the distance. And so this distance here is, of course, going to be a quantity. Here's going to be certain x. So this, if this is x and this is -1, that's good. The distance here from here to here is going to be x minus -1. And so setting up the cylindrical shells, the volume is going to be 2 pi, and then the radius, which is going to be x minus -1. And then the difference of the two functions, the function on top is x squared, 1 minus x squared, and the function below is going to be 1 minus x. And you can see that they intercept both in x equals 0 and x equals 1. So it's from 0 to 1. So at the very end, this is 0 to 1, 2 pi, x plus 1. And this is 1 minus x squared minus 1 plus x. So I get to cancel one of the ones. And then I'm going to have x minus x squared. And then I can simplify even more by multiplying this and this. So this is going to be x squared minus x cubed plus x minus x squared. And so now these two x squares are going to cancel each other. And it's going to be 0 to 1, 2 pi of x minus x cubed. And so that'll be 2 pi and x squared divided by 2 minus x to the 4 divided by 4 between 0 and 1. And of course, that's going to be 2 pi 1/2 minus 1 over 4. Or this is going to be 1 over 4. So everything ends up being pi half. And that is if I'm doing this in terms of cylindrical shells. If I use the same, but now I'm going to do washer method. So let's do a small one here. If I'm doing washer, then I'm gonna have to put everything in terms of y, because if I have the -1 axis here, then I want to have a perpendicular piece for the radius, and this is the internal radius, and this is the external radius. And so notice that this is y equals 1 minus x squared, but I can also see this as 1 y minus 1 equals minus x squared, or x squared equals 1 minus y. And so x is equals the square root of 1 minus y. And this is only the positive because it's in the top over here. So it's not gonna be the negative piece. And if this is y equals 1 minus x, then x is gonna be 1 minus y. And now the volume is going to be pi, and then again the limits are going to be from 0 to 1 in terms of y as well. It's 0 to 1 in x, 0 to 1 in y, and this is pi, and then the difference of the external radius square minus the internal radius square, and this is in terms of y. And so okay, so this is 0 to 1, and then the external radius is going to be 1 minus y minus 1, which is this, and then minus 1 minus y minus 1 x squared to y. So this is the setup for the same volume with the this or washers method. So now let's transition to improper integrals. So first we want to know if this integral here converges, but to be able to tell that, it will be very easy just to simplify this into a more convenient form. So as you see, this 1 over b squared plus 4b minus 5 can be seen as 1 over b minus 5 times b plus 1. Multiplication gets me minus 5, sum gets me 4, so actually gotta be b plus 5, b minus 1. And so because we have this, then you can probably guess that this is a partial fraction situation. And so it can be seen as this. And then you likely can find whatever this is going to be in terms of the coefficients. But notice that just because we know that this is this, that the integral from 2 to infinity is this, then you know that this is going to be a constant, this is going to be a constant, and this is going to be a log. So this is going to be equals to the limit when t goes to infinity of n is going to be log a log of b plus 5 when you pull between 2 and t. And same thing with this one, limit when t goes to infinity of b log of b minus 1 between 2 and t. So when we plug in t, we have a log here, and that log is going to go to infinity, and so this is going to be a divergent integral. Of course, you can go ahead and complete what the partial fractions is, but for this particular example, we don't really need to know what a and b are. We just can figure out that this is going to be divergent. Of course, it's worth mentioning that you should actually plug in t and minus plug in 2 as well to just verify what this integral is. Here, this is just a matter of checking really quick if the integral is going to be divergent or not. Now, for 14, you have a similar situation, but instead of going the limit when x goes to or t goes to infinity, we gotta go here with the discontinuity, which is 1. So this is the limit when t goes to 1 of 0 to t, 9 over 1 minus x squared dx. And so if you identify this, this is just like 9 times the arc sine of x is the antiderivative. The derivative of arc sine is 1 over 1 minus x squared. So the antiderivative of that will be just arc sine. And so between 0 and t. And so because we're doing the limit when t goes to 1 of that, we have 9 arc sine of t minus 9 arc sine of 0. And so this is going to be, of course, a number. And then we also gotta figure out what is arcsine of 1. We're going to assume that, of course, we are in the interval between minus pi half and pi half, which is where we can define the sine to be 1 to 1. And so being minus pi half to pi half, then we have that the arcsine of 1 is just going to be pi half. And the arcsine of 0 is just going to be 0, so this will be pi half. And overall, this is going to be a convergent integral. Now we want to use in the last one comparison criteria to find out why this function diverges. And so what we can start is with 1 minus x plus 1. And we want to be comparing this with something that is smaller. Of course, this is going to be bigger than 1, even if it's just for a little bit. Notice that e to the minus x is just going to be giving me a small value, but 1 plus that, this is still bigger than that. And so 1 over x is less than e to the minus x plus 1 over x. Now what happens is that the integral from 2 to infinity of 1 over x diverges. That's clear because this is the limit when t goes to infinity of 2 to t of 1 over x dx. But this is the log function, so this is a limit when t goes to infinity of log of t minus log of 2. And this goes to infinity, so that integral is divergent. And because this integral is divergent, but this is less than, then I have the situation where this occurs. And of course that means that the integral that we want to find out what happens diverges by criteria of comparison. Okay, so this is bigger than infinity, so this is going to be bigger than infinity and diverges. Okay, and so that's the end of the solutions for the worksheets of this week, and some of the exercises that you can use for the test preparation.